We're now heading into cosmology, which is the study of the universe itself. But before we get there, I've got a question. Here's our first lecture quiz question. How did we determine the mass of our galaxy? A, by comparing it to other galaxies whose mass is known. B, by looking at the motion of stars near the edge of the galaxy. Or C, through gravitational lensing of nearby stars. Go ahead and think about it, and we'll discuss in just a bit. Alright, so how did we determine the mass of our galaxy? It's all through the motion of stars. So if you remember back when we were talking about the Milky Way, we talked about how it is that we determine how stars are moving. And then the motion of the star, its orbit in the galaxy, tells us the amount of mass inside that star's orbit. So as we determine the orbit of the sun around the center of the galaxy, that tells us the amount of mass inside the sun's orbit. But the sun is absolutely not at the very edge of the galaxy, so it only gives us a portion of the mass of our galaxy. To get the mass of the entire thing, we have to determine the mass of the stars right at the very edge. Then as those orbit around, those will include all mass in our galaxy. So the correct answer is B, by looking at the motion of stars near the edge of our galaxy. So, to get a feel for the motion of stars, we create what are known as rotation curves. That's what we see here. So up and down, we have how fast the stars are moving, and then along the bottom, we have the distance from the center. So right here, we have the very, very center of our galaxy. This sudden ramp up in speed, this is the central bulge. There are so many stars all packed in close together that we get a huge ramp up in speed as we move out just a little bit because we're including so much more mass. Now, as we get out towards the edge of our galaxy, where as we step out more, we're not actually adding that much more mass to our galaxy, we would expect the stars to begin slowing down following Kepler's third law. So this dashed curve is what we expect based off of the amount of mass that we can actually see. The blue is what's actually going on. It is not actually dropping off as we would expect. Instead, it's leveling off or even increasing a little bit. Now, this is a problem because we know Kepler's laws, and we know that Kepler's laws are based off of Newton's laws, and Newton's laws are solid. So, we have one of two possibilities. Either, as we're getting farther and farther out towards the edge of the galaxy, we're including more and more mass, but it's of stuff that we cannot see, or our understanding of physics is wrong. Well, the leading kind of generally accepted idea is that we are including more and more matter. It's just of stuff we cannot see, but we give it a name to help ourselves feel better. We refer to it as dark matter. Now, based off of observations of objects out in the halo and the edge of the galaxy and so on, it appears that our Milky Way galaxy is at the center of an overall dark matter halo. And so we have this giant sphere of dark matter with our Milky Way located in the center. The halo extends over 100 kiloparsecs, meaning that it's much larger than just our galaxy. So although we have evidence that it exists, we still don't know exactly what it is. We'll talk more about that in a little bit. Now, one thing we can say for certain is that it is not luminous, meaning it's not giving off its own light. Now, the reason we know this is because if it was, we would see it and it wouldn't be a mystery. Now, as we look at other galaxies, so here we have rotation curves for 4 other spiral-type galaxies. Again, up and down, we have how fast the stars are orbiting, and along the bottom, we have their position in the galaxy. And notice that none of these galaxies have the drop-off that we would expect from Kepler's laws, meaning that all of these galaxies must have the exact same thing going on with them that is happening in the Milky Way. Well, based off of these rotation curves, it appears that galaxies have around 10 times more dark matter than luminous matter. So not only is dark matter there is a whole lot of it. We actually see very similar effects in ellipticals. You can't make a nice rotation curve like this for an elliptical galaxy, but there are other things we can do to do kind of the similar idea. And they also show the same amount of dark matter. All galaxies appear to contain dark matter, and quite a lot of it. So that was one way we have of determining mass of a galaxy, by looking at the motion of the stuff in the galaxy, the velocity. Now there's another way we can actually figure out masses. This is through gravitational lensing. So we've talked about gravitational lensing previously when we talked about black holes. So the idea actually comes from general relativity. Specifically, a massive object curves space-time, and as light travels, if space-time is curved, the light will also curve. In other words, we see an object bend the light. Okay? The object's gravity is actually bending the light. Well, depending on the size of objects and their orientation, it is possible that this bending of light can actually lead to multiple images. So, for example, here we have some very distant object, we have a massive galaxy, and then here's our point of view. Because of the gravitational pull of this galaxy, this star's light will bend a little bit on either side. So as we look at it, we see a double image of the more distant galaxy. Well, we've actually seen this. So here is the lensing galaxy, the ones that is bending the light, and here we have the double image of the more distant galaxy. Now, if the alignment isn't exactly right, instead of getting this nice double image, we'll get these streaks and arcs and curves and so on. But we can use these to help us figure out how much mass the lensing galaxy has, because it's all of the mass of that galaxy that does the bending. Well, as we determine the amount of mass in these galaxies that are bending the light, it's exactly what we get looking at the motion of the stars in the galaxy. These agree that there has to be around 10 times more dark matter than the luminous matter, than the glowing matter we can actually see in all of these galaxies. Now, this is a completely different method of determining how much mass there is, and both of our methods agree on the amount of mass that these galaxies have. For me, that pretty much indicates dark matter has to exist. Now, we can use this idea of gravitational lensing as we look at an entire galaxy cluster to start to figure out the amount of mass the entire cluster has. Well, when we do this, our dark matter problem actually gets worse. For a single galaxy, there's around 10 times more dark matter than luminous matter. When we get to the scale of a galaxy cluster, it's around 100 times more dark matter than the luminous matter we see. So again, dark matter exists, and there is a lot of it.